All right. All right, let's start with, okay, so I'm going to go way back to capacitors. I don't have a lot to say about capacitors, but I do want to show you guys a little bit. Right, so, do you guys see two parallel cylinders? Oh, and watch the spark here. Spark, right? So those parallel plates are like cylindrical shape. Uh, this could be called a Leyden jar. Ben Franklin and friends back in the 18th century would be playing around with these Leyden jars, right? Kind of like early. Well, it's not actually a battery. It's not chemical energy, but it's capacitors, right? So you could store energy in electric fields this way. Now, one thing he does here is he's pulling. I'm going to narrate for him. He's going to show that those metal plates don't actually carry the static electricity. I don't see any sparks, right? But he picks up this plexiglass separator, and he says this plexiglass separator feels all prickly. So the static charge actually built on that. Right. So there, so fun fact, right? Got another. Right. This guy's got what he's calling an ultra capacitor. Remember, I was telling you guys capacitance could be in farads, something like that. Now, there could be a pretty big capacitor just on a regular appliance, like an old TV set or something, right? You guys see so many microfarads. So 560 microfarads, that's like millionths of farads. And that's a pretty big capacitor. But this guy has 2,000 and some farads. Woo! So it's like a billion times the capacitance. All right, good. All right, so what's he going to do with this? Oh, he does a little bit of math. He said, how much energy could you store in a capacitor? So 1/2 capacitance times voltage squared. Great, we're going to store some energy in there. Right? And then get some sparks, we're going to get all that energy out. And then this video, he melts a bunch of stuff and does some math along the way too. Let's see if he melts some more stuff. So, yeah, okay. He has a bunch of wired up together. Right, so even more capacitance. All right. I think it's about all I got to say on capacitors, though, about all that. Right. A Faraday flashlight had a capacitor. Right. Let's switch over to magnetic field. Right. So you guys saw my 3D magnetic field. He's going to take a paper, throw some iron filings on it, boom, right? There's like a 2D cross section, right? And then the convention people came up with is to draw the field lines from north to south, right? So, okay, so now we have a conventional direction, right? So now when you go to apply the right hand rule and try to figure out like, which way are these vectors pointing, or which way is the force going to be on the motor, right? Well, if you know which way is north and south on a magnet, that'll help you figure that out, right? Next one, let's look at flux. Right, so there's B magnetic field. So imagine there's a big old magnet on the left side. Got these approximately parallel magnetic field lines. And let's have those magnetic field lines go through some area we've roped off, so that red area. Now, you could outline the perimeter of that rectangle with a wire, right? And now you're setting up either a generator or a motor, depending on which way you're going with this. Okay. If you increase the area, you increase the flux. So here's Greek letter phi to represent flux, right? So flux is field times area, but it's really a dot product. So notice if you have the area aligned so that none of the field lines go through it, that's zero flux, right? Well, if you turn this upside down, then you have negative flux. Okay, so tomorrow when you guys build a motor, right, and that motor is spinning, right? I bet it's going to be oscillating between positive and negative flux. One last idea is, what if you have a weird shape? Like, what if it's not a flat plane for the area? What if it's all wonky like that? Right? And very simply, all it is like if you were standing in the back and looking straight on, like straight ahead, and it looked like a flat plane, it would just be equivalent to that, right? So they do some fancy calculus here, saying, well, what if I break up to like 10 by 10, like 100 little tiny squares, so you do each one, right, and do a dot product. But if effectively it's the same as just having a flat plane looking head on. Okay. Let's look inside the Earth. Right. So why does Earth have a magnetic field? Right. So the main theory. Oh, this is not gonna. Oh, here we go. So right. Main theory is the fact that Earth has a molten mantle, and that there would be these convection currents set up, right? And there's ferromagnetic materials inside the Earth. Right. Sets up a weak magnetic field. Right, which is good for us because that protects us from a lot of dangerous cosmic rays. I want to play this. There we go. Right. So if the sun's on the left, there's a little tiny Earth. There's day and night. Right. And here's Earth's magnetosphere protecting us from X-rays, gamma rays that be coming from the sun. Right, things like that. Maybe a UV. Right. So back to going on inside the Earth. Right. Now one of the main points of evidence for this theory, like why Earth has this magnetic field from this, is if you look at counterexamples like the moon or Mars, right? Mars used to have a magnetic field, and here's how we know that, right? Because if you look at the surface of Mars, you see a lot of evidence of water erosion, right? But Mars has almost no water on it. I mean, they found little tiny traces of water here and there, but almost none. But Mars used to be covered by water just like the Earth is. So what happened? Well, Mars is physically smaller than the Earth, right? You guys know what the Earth has like geothermal energy, right? You can tap into geothermal, right? Up in Iceland, they get a lot of energy that way, right? Well, okay, so all this molten mantle, it's really hot. It's slowly leaking, like radiating energy out, right? And if you run the clock like a couple billion years, eventually the Earth is going to cool down. It's going to solidify. Mars already went through that entire process because it's a smaller planet. And so Mars must have had some molten mantle, like let's say probably a couple billion years ago, that has since solidified over. And now Mars lost its magnetosphere. And so Mars's atmosphere got almost entirely picked off. Now Mars does have an atmosphere, but it's really thin compared to Earth. I think it's like 1% of Earth's atmosphere or something like that, right? Um, and so whatever water Mars used to have on it has since like evaporated into space. Right? So what's happened. Okay. Now there's different kinds of magnetism. You normally think of like ferromagnetism, right? You can like pick up anything with iron in it with a magnet, right? Uh, Water is also magnetic, but it's a different kind of magnetism. It's called diamagnetic. Water actually repels from magnetic field. If you have a really strong magnet in like a bowl of water, you might possibly be able to see it. If you put a magnet near the surface of water, it'll push the water down a little bit. Now this frog is mostly made out of water, so if you put the frog in a really strong magnetic field, it'll be floating around. Um, I think it's just along for a fun ride. I don't think it's hurt or anything, but yeah, you do that. I think it's mostly water in it. All right, let's do. I was going to show you guys electric motor. Right. So I showed you guys building an electric motor. Remember, if you run a current through a coil of wires and put that next to a magnetic field, that will create a physical force. Oh, wait, is that this one? Oh, okay, so basically that. There's an animation of what I was just showing you guys. Right. So I'm gonna have you guys build that tomorrow. All right, let's watch some Paul Hewitts. Paul Hewitts. That is pretty neat. All right. So we got inductors. There you go. Coil of wires, right? You guys saw all those coils of wires. Right, so you run a current through it, and those blue lines, that's a magnetic field. Right? Hey, that's an electromagnet. That's the electromagnet that I was showing you at the beginning of class, and that you guys are going to create tomorrow. Electromagnet. Right. So there you go. Oh, and like I was saying too, look at that. Right, it causes the current to lag. So you flip up the on switch, close the circuit, and it takes a while for the current to build up. Open the circuit, takes a while for the current to go to zero, right? And with this, you can transmit electricity wirelessly, or does it show some, here we go, here's inductive coupling. You see there's a couple of inductors there. It's gonna show them separated. Oh, there it is. So two inductors. You see how they're not touching at all, right? So there's a current flowing through the bottom one, and it's transmitting a magnetic field and therefore a current into the top one. So he's picking up there. That's what we got. Actually, I got maybe a better example is this next one. Yeah, this one right here. So, look, a big copper ring. That could be a giant inductor, basically, right? You just turn the on switch. Okay, so now we've got some current flowing through. You got this little green LED light up. And on the right side, watch this bulb. Bam, turns on. Because this current on the left side creates a magnetic field. The magnetic field picked up on the one on the right creates a new current. Well, look at that. He moves it closer, it gets brighter. Ooh, look at that. Closer is brighter. Right. And then let's see, throughout this, did you guys see it blink off at some point? At some orientations, like at 90 degrees, like that, didn't turn it on at all. Because now the magnetic field and therefore the current doesn't transfer. Right. Okay, so these have to align. Right. How about next one? Induction heater. Watch closely. How about listen closely? Induction heater. Uh, yeah. All right. Thanksgiving. There you go. Next time. Spring inductor. Thanksgiving. Right, here's Lenz's law. Notice that magnet is not attracted to that copper casing, right? But drop it through, and it takes forever to fall through. There's no friction going on there. So this is Lenz's law. So you got the magnet falling through the closed. It has to be a closed loop of copper casing. If it was like a C shape, it wouldn't work. Right? It has to be a closed loop. Right? That creates eddy current, which creates its own magnetic field, which resists the original magnetic field. Now the generator application of this is how most electricity is generated, right? Push a wire past a magnet. Is there's going to be a resistive force, which reflects the energy that's being transferred onto the grid in the first place, right? Like if it weren't for that, like if that didn't happen, what you were seeing right there, then you could like create energy for free, sort of like if it worked at all to generate electricity. There's Lenz's law. Let's look at a different motor design. Right, so you guys see magnets, batteries, a voltage source, wire, gonna connect, right? And creates a force, causes rotation. It's going clockwise from above. Right? Now, guys, what if you flipped the battery? Do you think it would flip back the other way counterclockwise? Right? Or if you flip the magnets, right? So directions matter. I'm thinking right-hand rule. Right? Is this kind of right? Where's my sound? All right, you guys have a great day.